All right, so here we are looking at some homework problems that I'm assigning to my students that correspond to Chapter 3, Section 7. And first part of this is hiding behind me a little bit. So what I'm going to do is just walk through and talk about like a little bit of concept, a little bit of strategy, how to get these things started. As I said at the beginning of the previous video, where I went through the notes on this section, a big component of this for you is going to be taking these problems and relating them over to problems from those notes, or of the problem types that I didn't cover. You're going to need to go into the downloadable notes, which are going to show up as PowerPoint slides, I believe, or you can go into the actual ebook where you're going to see even more articulation and explanation of what's going on in these solution processes. But remember that the sort of common thread through the problems that we looked at in the previous video were that the solution process started with looking at the problem, framing it up using the difference quotient as a fraction, and then applying the limit so that the denominator headed off towards 0. Or in the last example that we used for marginal cost, we sent the denominator to 1. So in effect, we were taking the derivative, and then we had to plug in appropriate values and interpret the results that we got from those. So let's keep that in mind as we go through all of these problems in this homework assignment, and let's see what we got. Let's see what we're looking at in this assignment. So the first problem says that we've got a particle. It's moving according to the law of motion. So we have one of these S equals equations. It's a function of time. It says S equals f of t. Time is greater than or equal to 0, so we're not going to be going back in time in this problem, as much fun as that might be. T is measured in seconds, S is measured in feet, and we want to find, remember that f of t, I don't know why they don't just call it S of t, but f of t is our position function. We want to find the velocity at time t. All you need to do is take the first derivative to get your velocity equation. What is the velocity after 1 second? It tells you what to do here. Plug in a 1 into your v equals, or your v of t equation, or function. When is the particle at rest? We saw an example in the previous video. Your particle is at rest when your velocity is equal to 0. So take your velocity equation, set it equal to 0. This one's very similar to the last one that we saw. This is a cubic, so your velocity equation is a quadratic. Set it equal to 0. Factor, probably, and find your couple of t values. When is the particle moving in the positive direction? When your velocity is greater than 0. I plotted in the previous video, we looked at where on the horizontal axis our t values were equal to 0. I drew a parabola through those because my velocity equation was a quadratic. We looked at where the arms, so to speak, of that parabola were above the horizontal axis, and those were the intervals on which velocity was positive and therefore had our particle moving in the positive direction. Total distance traveled during the first 6 seconds. I'm not going to talk much more about this problem. This is so analogous to the problem that we saw in the previous video. You're going to have to liken it back to that one. Don't forget to chop up your domain and look at change in distance from t equals 0 to t equals 6. That's what's happening in part E. And then add them up. Part F, draw a diagram. We saw that also in the previous video. Where your velocity is positive, it has you moving to the right. Where velocity is negative, it's moving to the left. Where velocity was equal to 0, at those time values, you're making a U-turn. So check that out and make sure that it's specific to the interval from 0 to 6. Find the acceleration at time t. Your acceleration equation is the derivative of your velocity equation. So you just have to calculate another derivative there and then plug in a t value of 1. Use a grapher or an online graphing utility to get your 3 graphs. experiment with changing your window. I'm going to do that in a problem that's coming up here momentarily. When is the particle speeding up? When is it slowing down? We've talked about that already. Velocity and acceleration either both need to be positive or both need to be negative. You're answering using interval notation. And then here is a separate question. This is question number 2 in my homework assignment. The graphs of the velocity functions of 2 particles are shown. Here's one, there's the other one. So let's just look at the first one. T is measured in seconds. When is the particle in figure A speeding up? Remember that a particle is speeding up or accelerating. No. A particle is speeding up when the acceleration and velocity are either both positive or both negative. But we only have the graph of our velocity function here. So how am I supposed to tell where the acceleration is positive? Clearly, I can see where the velocity is positive. It's from 0 to 2, right? This part here is where velocity is positive because it's above the t-axis. But how do I know where acceleration is positive? Remember that acceleration is the first derivative of velocity, which is the rate of change of velocity, which is the slope of the tangent line to the velocity curve. So where here does your velocity graph have a tangent line with a positive slope? I would say here you have a positive sloping tangent line, here positive sloping, here positive sloping, all the way up until you get to here. At this point, the slope of your tangent line looks like it's 0. So from 0 to 1, your acceleration is positive. Here, however, your acceleration is negative. That also makes sense because your velocity is decreasing. So it makes sense that your acceleration would be in the negative direction. That's dragging your velocity down. So here, your acceleration is less than 0. Here also, your acceleration is less than 0 because it's a negative sloping tangent line, negative sloping tangent to the velocity curve. So we're describing acceleration. Except here, where a is less than 0, v is also less than 0. So again, you're speeding up when velocity and acceleration are both positive or both negative. Make sure you answer using interval notation. Well, I'll tell you, the answer to this first one is, at least in this example, it's speeding up from 0 to 1 on the time interval from 0 to 1. You're going to want to look in the ebook or into the notes and confirm whether the interval notation should be using parentheses or square brackets. I would tend to use parentheses, especially up here. I don't want to include the point where we're making the U-turn because there, acceleration is equal to 0. Even though velocity is positive, acceleration is not positive, it's 0. So I would exclude that point, and part of my answer would probably go from 0 to 1. That wasn't much of a 1. There we go. Slowing down, acceleration and velocity need to have opposite signs. And then you'll go through that whole examination process and draw some tangent lines on this curve also. The tangent lines will be modeling acceleration. In question number 3, we've got projectile motion. So we've got the height of a projectile shot vertically from a point 4 meters above ground level. Just FYI, that 4 meters is this 4 meters. A way that you can remember that is that if you take a t value of 0, so when you're right at the start of this flight of this projectile and t is equal to 0, both of these terms cancel out, leaving you with h equals 4. So h of 0 equals 4, or height at time 0 equals 4. Ground level initial velocity, 25.5 meters per second. You can bet that this 25.5 and this 25.5 are the same. That's your height function after 2 seconds. Height is the same thing as saying position. So in order to find the velocity after 2 seconds and 4 seconds, you'll need to take the derivative of your height function. So v of t will equal dh over dt, the derivative of your height equation. You'll have to plug in a 2 and a 4 for t once you get that derivative. All right, so that'll be your two velocities. When does the projectile reach its maximum height? Now look at the original height equation. Also, visualize a projectile being shot vertically upward. Obviously, the flight path is going to go up, and then it's going to come down again. So they're saying, when does it reach its maximum height? We're going to answer using a t value, a time value measured in seconds, and it's going to reach the maximum height when velocity equals 0. On the way up, our velocity is positive. On the way down, our velocity is negative. Right at the top, our velocity is going to be 0. So take your velocity equation, set it equal to 0, and solve for t. That's going to give you that answer. What is the maximum height? Well, you know when the maximum height occurs. Wouldn't it be nice if you had a function that described height, into which you could plug that time value? Okay, got that? Good. When does it hit the ground? Well, certainly this thing is not starting on the ground. We were told that it's starting 4 meters above the ground. It's going to hit the ground when h does actually equal 0. So you have to take your height equation, set it equal to 0, and solve for t. Now you might think that's going to be a little bit challenging. That's a quadratic equation with a negative leading coefficient of negative 4.9. That's going to be a little tricky. Your options are to use the quadratic formula, which will work. I don't think that you want to try to factor that equation. Negative 4.9t squared plus 25.5t plus 4. Factoring that would be a bit of a nightmare. Your other option is to use a grapher. And if you graph that function, your flight path is going to look something like this. And when you graph it, it's going to graph the entire parabola. So you might want to change your window so that it's not distracting and so that you're only looking at t values or x values that are greater than 0. And you should probably only be looking at h values that are greater than 0. And this is an instance where you could change your settings on your graph so that you're only looking at y values that are 0 and larger, but you might want to drop those x values and y values, back them off to like -1 or -2, just so that you can make sure you're seeing the x and y axes on the screen. Otherwise, it gets a little disorienting. Then, if you, in Desmos, you might be able to just come in here. Don't know why that happened, sorry. You might be able to just come in here and click, and it will tell you what your coordinates are at that point. Remember that your x coordinate is your t value and your y coordinate is your h value. So that would be when it's going to hit the ground. On a graphing calculator, you might also have to graph y equals 0. And when you graph y equals 0, that's going to put this line on here, and then you'll want to find the point of intersection of your parabola and your horizontal line y equals 0. If you don't know how to do that in a TI 83 or 4 or 5 or 7 or 9 or whatever they are now, look up a video how to find the intersection or how to use intersect on a TI 84 graphing calculator. The function, I don't have my grapher with me. I think it's just called intersect. Yeah, you have to use like the trace button or the calc button or something, which might use the second function, and then you tap into that top row of buttons on the calculator. You can find it though, intersect mode on the TI graphers. So when does it hit the ground? You'll have a time value. That's the answer to part D. With what velocity does it hit the ground? You take that time value, plug it into the velocity function. You'll have your velocity when it hits the ground. Ball's thrown vertically. What is the maximum height reached by the ball velocity? What is the velocity? So part A, you know how to do that now. Set v equal to 0. What's the velocity of the ball when it is 320 feet above the ground on its way up? The way that part B is phrased tells me that this object is going to pass through a height of 320 feet above the ground. It's going to reach some other maximum y value or height value, and then on its way down, it's also going to cross through a point where it's 320 feet above the ground. I believe this is the function that I graphed in Desmos earlier. Let's take a look. Here it is. So when I first graphed this, let me hide myself there. Can I? I don't see a reset button on here. Oh, zoom square, that might do it. Right, so when I first graphed this thing, it looked like, I don't know, like this, right? I can see that there's some red on there. That's my curve, but it doesn't help me very much. So what I did in the top right corner, it's just on the edge of the screen, the way that I have this cast into this video, there's a little wrench up there in the top right corner above the plus sign, below the globe in the top right corner. And if you click on that wrench, it gives you this little pop-out menu. And what I did is I changed my X values. You can see these 3 check marks going down the left-hand side of that little pop-out. One of the check marks is next to X-axis. Below where it says X-axis, I'm going to come in here and I'm going to change this to, let's change it to 0. Ooh, now my parabola is, sort of going off the left-hand side of the screen. But I've got a lot of white space to the right of my whole parabola. So let's take the X values up to like 14. That'll keep us, can you see what I'm clicking on here? Not so much. All right, let me bring that menu back up. I'm going to change my X value so that it maxes out at 14. Okay, and now my Y values, my parabola is off the charts here. Let's get these Y values up there. Let's take them up to 200. Oh, now we're starting to see the thing better. So we could just keep adjusting these and adjusting these. The other thing that you could do is, again, on the right-hand edge of the screen, hit that minus sign near the top right and just zoom it out too far, okay? Or you can, on my tablet, I'm able to just pinch to zoom, which is nice. Okay, so I can see that this thing tops out somewhere between 3 and 350, and but my horizontal axis, side to side, I've got a lot of space. I wish I could just zoom in sideways, but you notice that as I zoom in on the x-axis, and I can see that I have an intercept over here at 0, 0, and to the right I can see I've got an intercept at 9, 0. Now that those are fit nicely on the screen, the top half of my parabola is off the screen. This is when it's nice to now hit that little wrench in the top right corner, and under where it says y-axis, change that y, the larger of those two y values, take it to 350. Now I've got the whole parabola on the screen. I can click on my x-intercept a couple of times and it pins those values. I click on that right hand x-intercept at 9, 0. Click on that, it pins that value, and you can see right at the top of this curve, there's a little gray dot. If I click on that, it's going to hold that number there for me also. So at 4.5 seconds into my flight path, I reach a maximum height of 324 feet. Now, let me go back over to the question. Remember that height of positive 324 feet. My question said, oh boy, be right back. There we go. So back in the original problem, you see that, oops, I think it was the next one. What is the velocity of the ball when it is 320 feet above the ground on its way up? $320. Let's open up our equations on the left-hand side, and I'm going to click on equation number 2, and I'm going to graph the line y equals 320. Enter. I didn't have to click enter. And back over here on my graph, we can now see very clearly that there's a point here where it hits a height of 320 on the way up, and there's a point where it hits 320 on the way down. And those are happening at 4 and 5 seconds into the flight path. Let's see if this is going to work this time. It did work. It did work. Okay. So the velocity of the ball when it is 320 feet above the ground. If you take your position function, s equals 144t minus 16t squared, and you set it equal to 320 feet, and you solve it, I would subtract 320 from both sides. So I'm taking this 320, plugging it in for s, and then I'm going to subtract 320 from both sides. I get 0 equals, I'm going to switch the order of these terms around, negative 16t squared plus 144t, and then I subtracted the 320 from both sides, so minus 320. If I solve that equation, and you should be able to divide, let's see, 144 is 12 times 12. Each of those 12s has a 4 in it. Borrow the 12s. That makes 16. Great. So this is divisible by 16. This is divisible by 16. This is definitely divisible by 16. That would give you a 20. I would divide the whole equation by negative 16. And then you're going to have a really, at least with these numbers, you're going to end up with a really manageable equation. If you solve that for t, you're going to get those two t values that we saw, the times when we have a height of 320. You want to use the lesser of those two t values because you're interested in the velocity of the ball when its height is 320 feet above the ground on its way up. That was the first of those t values. The second t value is when it hits 320 on its way down. Once you have that t value for whatever problem, whatever numbers you have in your version of this problem, once you have that t value, you can take it and plug it into your velocity equation in order to find the velocity at that point in time. Do you have your velocity equation yet? You do, because to answer part A, you took the derivative of your position equation and set it equal to 0. What's the velocity of the ball? At 320 on its way down, plug in the second time value. Average rate of change, that's y2 minus y1 over x2 minus x1. Part B, instantaneous rate of change. Take your original equation and set it, take the derivative and plug in an r value of 5. So we've transitioned a little bit. This question, find the average rate of change of the area of a circle with respect to its radius r as it changes from 5 to these various numbers. So the area of a circle is equal to pi r squared. In order to answer this question, the average rate of change would be the area when your radius is 6 minus the area when your radius is 5 divided by the change in time, which would be 6 minus 5. The 6 that's in here, that came from here, is going to change into a 5.5 and then a 5.1. The instantaneous rate of change, so you'll have to do those three very basic calculations. Does it say? This question does not tell us specifically whether we should be answering rounded to a certain number of decimal places or if we should be answering using an exact value. I would try answering exactly in terms of pi, when you click into those text entry boxes, you should get a pop-up, a little toolbar where you have access to the pi symbol. For part B, you want to take the derivative of this equation. You'll get a prime and then plug in a 5. Still answer in terms of pi. At least that's my guess. Number 6, the mass of the part of a metal rod. Great, refer to the previous video. Instead of using the square root of x, in this problem we're using a function 2x squared is your mass equation. Problem number 7, you should also look into the book or the notes. Boyle's law is an equation which helps you look at pressure and temperature and volume. So it's an equation PV equals C that relates those three values to each other. In part A, you're being asked to find the rate of change of volume with respect to pressure. This says dV dP. You've maybe never seen a dV dP equation before, so I'll liken it to something that you're familiar with, like dy dx. What kind of equation are you working on when you're asked to find dy over dx? Usually you're working on an equation that looks something like y equals maybe like ax squared plus bx plus c. Or something like that, some kind of a y equals equation. Well, if I'm going to be calculating dV dP, I should probably have an equation that says V equals. You should modify this equation then to say V equals. Not just for this equation, but I'm trying to teach you a general strategy that will work for you regardless of what your initial equation is. If it says dV on the top, I recommend, probably, not all of the time, that you make your original equation say V equals. In this case, that's very easily done. V equals C over P. Can we now take the derivative with respect to P? Well, we can. When it was dy over dx, my x variable was all over the place on the right-hand side of my equation, and I would take my exponent and multiply it by whatever number a was. A is a number. In this PVC equation, in Boyle's law, we're taking the derivative of v, which is good. We've got v all alone on the left-hand side, with respect to p. So p is what we're considering the variable on the right-hand side. Well, if that's the case, then what the heck is c? It's the same thing as a and b and c over here. It's an unknown constant value. Just in your mind, pretend that it's a number, okay? Therefore, maybe it would be helpful for you to write this equation as v equals c times p to the negative first power, or c times 1 over p, whatever is going to make it easiest for you to take the derivative. If it were me, I think I would go this route. All right. Take the exponent, multiply it by the coefficient, and decrease the exponent by 1. A sample of gas in a container, low pressure, steadily increasing temperature for 16 minutes. All right, 16 minutes, that's a time value. Is the volume decreasing more rapidly at the beginning or the end of the 16 minutes? So as it says, from the formula that we just calculated, dv over dp, we see that as p increases, so this kind of prompting is nice. As p increases, let's just go ahead and maybe calculate this. I'm trying not to do all the work for you, is why I keep sort of stalling here. What we calculated up here is still just the right-hand side of our v equals equation. When you take the derivative of that equation, your p variable will still be in the denominator. I'm not going to tell you exactly what it looks like because this is not much of a algorithmically modified question. So everybody's version of this question is going to look pretty much the same. But I'll tell you that p is still going to be in the denominator. And what happens to the value of a fraction as your denominator gets bigger? Compare like 1 over 2, compare that to 1 over 10. How do the numbers 1/2 and 1/10 compare? As the denominator gets bigger, what happens to the value of the whole fraction? All right, so this is saying that from the formula for dv over dp, we see that as p increases, the absolute value of dv over dp, so you have to frame that up, put the absolute value bars, write the function inside of there, think about what's happening as my denominator is getting larger, what's happening to the value of that whole fraction as the denominator gets larger. Thus, the volume it's either going to be increasing, decreasing, or staying the same more rapidly at the beginning. So we're comparing as time is moving on, as our p value is increasing, as the pressure is increasing, the rate of change of volume with respect to pressure is also changing. So there's a lot of change happening in this problem, but try to go through and just write a couple of things out and be thinking about the different relationships of what's changing and how, as that thing changes, it affects the other values that are part of the dv dp equation, rate of change of volume with respect to pressure. Write the formula for isothermal compressibility. See this example in terms of p. So I didn't actually look at that. It's in the notes. It's for sure in the textbook. You should be able to click into that example. I have not actually done that and model what's going on in that example. And that's the last problem in that homework set, which means I am out of here. I'm not really out of here. I'll be wearing the same shirt in the next video. More videos to come. So I will see you over there. Thanks.